Hi everybody, let's talk about motion control. It's John from Additive Alliance, continuing my series on building a 3D printer from scratch. When it comes to motion control, you have a bunch of choices. The first choice to make is whether or not you want stepper control using stepper motors or servo controls using servos and encoders. I'm not going to discuss servos at length here. They tend to be more accurate and can potentially be faster than steppers and even have more power to them because they don't hit that RPM threshold that steppers do. But they're more complicated and it's a little harder to design systems that work with them. So we're going to focus on steppers. Stepper motors are more than adequate, more than accurate enough for most 3D printer designs, and you can get lots of speed out of them, but you do have to be aware that their torque drops off as their RPMs increase. So you need to look at the curve of the motor you're using and make sure you're using motors that are appropriate for the masses that you're translating. Then it comes down to how you control those stepper motors. There are lots of ways, and the most bare bones way would be to use an individual driver for each axis, each motor. You can buy these TMC 2209 type drivers for about $5 each, and they are an individual stepper driver which will produce the four signals you need, the AA prime, BB prime, to drive a stepper motor from something like a Raspberry Pi or like an Arduino by simply enabling the chip and sending the number of steps that you want to it. They're very simple to use and very straightforward. However, they're very crude. In other words, you have to do a lot of programming if you're going to want to coordinate multiple axes. For example, think of just having a system that uses these for your X, Y, and Z. If you just want to make a pure X move, it's simple. You just send a number of steps to the X driver. But if you want to make a, say, 45-degree move in X and Y, you then have to send the same signals to X and Y drivers, have them start simultaneously so that they maintain the same position along the 45. And you can see this starts getting more complicated when you start having off angles like 30 degrees, because you want them again to start that line at the same time and finish the line at the same time. So then that means that the motors are actually moving at different speeds. So then you have to think about dominant axis. You have to use what's called a tangent ROM to look up what the split in power is going to be, or number of steps between each motor. It gets complicated fast. They also don't have any kind of acceleration control per se, so you have to build your own ramps and software on how you're going to accelerate it and de-accelerate it. Simpler solution, albeit more expensive, is to buy a board that actually has controlled coordinated motion built into it. On our NX3D case study right here, I settled in on a Tiny G made by Synthetos. It's I have it upside down. It's about $130, $140. But this guy is a huge time saver and works really well. It's a 4-channel board that controls 4 steppers, 1, 2, 3, and 4, with a host of other inputs for limit switches, for fan control, for other types of inputs. And what it does is that it actually coordinates the motion. So you would send it coordinates through G-code from point A to point B, and it will actually set up the right number of steps and the right timing for all 4 axes. The 4th axis being something like material delivery. In this case, it's the drive for the FDM filament. So you have X, Y, and Z, and say FDM filament. And it is even possible to get 5th and 6th axes out of these by using relay switches, where you can take something like the A axis and have it be dual, or turn one on or turn one off. They also have a huge advantage in that they have acceleration control. I think the Tiny G is 6th order, maybe even 7th order. So if you think of velocity being the first derivative, time acceleration being the second derivative, these are going all the way down to like the 6th derivative. So it's not like some derivative of the impulse. And what that does is it produces an S curve for the acceleration ramp, which means it's very smooth to accelerate when it goes up to max velocity, and then it's very smooth to deaccelerate. That translates into smooth cornering, which is an absolute necessity when you're drawing complex 3D parts with filament. And that ultimately leads to higher accuracy and higher surface quality. So there are other coordinated motion boards out there, some cheaper than the Tiny G. The Tiny G is kind of a deluxe version, but I think it's well worth it because of the type of motion and type of acceleration it provides. So it takes a lot of programming and effort off the table by simply issuing G-code commands. You see it running right now, building a benchy. That particular benchy in PLA is a 2-wall 10% dense benchy, and this machine builds it in 40 minutes, which is reasonably quick. It's not going to set any benchy speed competition records, but it'll be a nice looking model, and it's relatively speedy compared to most other machines that are out there. That's it, motion control in a nutshell. I'll do another video about motors and belts versus say a lead screw drive or some other types of drives. So stay tuned for that. But if you have questions on motion control drivers, just go ahead and hit me up in the comment section, and I will promptly get back to them, possibly make another video if somebody can throw me something really interesting. Cheers.